Welcome back all of you. In this video lecture we'll discuss some of the conceptual questions based on the concepts that we studied in number 2. So beginning with the first question, that is, we're given with the signal yt that is equal to e raised to the minus t. And the question is, show that yt is of the form a into e raised to the minus t for t 0 to 3 and determine the value of a. This is the given question. If you look at the statement of the question, we are given with a signal. We need to just manipulate this mathematical expression of the signal yt such that we make it equivalent to this simplified form, that is a into e raised to the minus t, and next we find out the value of a. And the condition given is that the range of t should be from 0 to 3. So we need to just manipulate this mathematical expression. That is what we have to do in this question. So let us try to simplify it now. Yt is equal to e raised to the minus t convolution summation del t minus k ranging from minus infinity to infinity. Now if we just change the order of the summation, which we can easily do it, the summation, and we're left with e raised to the minus t dt convolution with del t minus 3k. Alright. Now let's say this is some signal, some third signal, that is x of t, and we are convolving x of t with del t minus 3k. We've already seen the properties of convolution operator with the impulse function. If any signal xt is convolved with such a signal del t minus 3k, the resultant will be x t minus 3k. Okay, so we'll make use of the same property over here in this question, and hence the resultant will be summation k ranging from minus infinity to plus infinity e raised to power minus t minus 3k. will replace the argument t by since xt, this is your xt signal, xt gets converted to xt minus 3k, the argument t is getting replaced by t minus 3k. So in xt, which is this e raised to power minus t ut, will replace the argument t by t minus 3k. This is the simplified expression now. Now let us further simplify it. Now this is a exponential signal which is being multiplied by a shifted unit step function. Alright, so we can simplify this expression as summation k ranging from minus infinity to infinity e raised to power minus t minus 3k into 1 for the range t minus 3k greater than 0, which is also equivalent to t ranging from t greater than 3 of k, right, and 0 otherwise. You can easily rewrite this equation as this, because this exponential function is being multiplied by a shifted unit step function, and the shift is by 3k. So this ut minus 3k means for t minus 3k greater than 0, this unit step function, the value of unit step function will be a unity, and for the other values this will be 0. So we are doing the same thing over there. Okay, now this is the expression of yt, simplified expression of yt for this range t greater than 3k, the value is this, and for the other values of t it is 0. Now in the question we know that the condition given is that t should be in the range of 0 to 3. So now to determine yt, y of t over interval t ranging from 0 to 3, the value of k should be, let us see the value of k. What should be the value of k? The value of k should be Here, either it can be 0 or -1, -2, and so on. If you put the value of 0 over here, t will be greater than 0, and that lies in the given range, which is 0 to 3. This is the given range. We need to find out the expression of yt in this range only. And if the t is -1, the value of k is -1, then t will be greater than -3. For -1, value of k as -1, t will be less than 3, and so on. So if you'll see that for these values of k, the given range is being satisfied. That is, the value of t lies between 0 to 3 for this given set of values of k. Hence, the resultant yt can be written as summation k ranging from -infinity to 0 e raised to power minus t minus 3k, and the range is t 0 to 3 and 0 otherwise. Let us further simplify it, because our aim is to simplify yt in the form of a times of e raised to power minus t. So we need to further simplify it. Let's do that. E raised to power minus t summation apply this summation expression over here. So it becomes e raised to power minus t summation k ranging from 0 to infinity. Will change the order of the summation. And hence y of t can be written as equal to e raised to power minus t into 1 divided by 1 minus e raised to power minus t. It is a infinite GP. We are applying the summation formula, that is p upon 1 minus r. And so this becomes the final expression. If we compare it with a into e raised to minus t, we can say that the value of a is equal to 1 upon 1 minus e raised to minus t. This is the value of a, and this is how we are able to prove that this yt expression can be written in this simplified form, e into e raised to minus t. Moving on to the next question. Evaluate the step response for the LTI systems given with impulse responses as. So we are given with the impulse responses of several LTI systems, and we need to find out the step response. So the impulse response is given are so these are the 5 LTI systems whose impulse responses are given to us, and we need to evaluate the step response of these systems. Now let us first analyze what do we mean by a step response. If we have a LTI system with impulse response, let's say h of t or h of n, depending on the continuous time or discrete time system, xt is the input and yt is the output. So step response means the output or response of the system when the input is a unit step function. That means it is the response when the input signal applied is u of t, unit step function. Okay, so let us do the first part of this question. The impulse response of a discrete time LTI system is given as this, and we need to find out the step response. Okay, that means the input signal x of n we know will be u of n. So if we try to simplify the system expression, we'll see that, let's say S of n is the step response, that is the output of this system. This S of n will be equivalent to H of n, which is the impulse response convolution, with X of n, which is equal to Un. Right? And this can be simplified as the summation k minus infinity to infinity H of k U of n minus k. Okay, and U of n minus k can be written as 1 or 0 for the ranges when k is less than or equal to n, when k is greater than n. Right? So we have that S of n is nothing but is equal to summation. The range will remain same, H of k. So it will be this Un minus k can be replaced by unity, and so yeah, this range will change from minus infinity to n, not minus infinity to infinity. The range will change accordingly, because for the rest of the range, that is for k greater than n, it is 0, and for k less than or equal to n, that is from minus infinity to n, its value is 1. Okay, so the step response is nothing but summation of the impulse response. This is the step response, and this is the impulse response. Now moving back to the our question, S of n will be equivalent to summation k ranging from minus infinity to n H of k, and H of k for this question is minus 1 by 2 raised to power k U of k ranging from minus infinity to n. Let us change the range of this summation according to this U of k, because U of k will be unity for k greater than 0 and 0 otherwise. So the summation range will change from k is equal to 0 to n minus 1 by 2 raised to power k. Right? Now this is a finite GP, and if we simplify it, it becomes 1 minus 1 by 2 raised to power n plus 1 divided by 1 minus 1 by 2. And if we further simplify this, we get 2 by 3 plus 1 by 3 into minus 1 by 2 raised to power n. This is the final answer, that is the step response for the given system. Similarly, let us do the second part of the question, in which the impulse response is given as H of n equal to del of n minus del of n minus 2, and again we need to find out S of n, and which is the step response. And in the previous part we've seen that the step response is nothing but summation k ranging from minus infinity to n H of k. H of k is given to us as del n minus del n minus 2. Substituting this, further simplifying it, so this we can simplify it further. Del of k minus summation del of k minus 2, and this summation we know it is nothing but equivalent to U of n, and this is equal to U of n minus 2. This property we have already seen, that summation of impulse function is nothing but your unit step function. So this is the step response for the second part. Let us do the third part now. The third part, the impulse function is given as H of n equal to minus 1 raised to power n U of n plus 2 minus U of n minus 3. Alright. Again, we'll use the same relationship, that the step response is nothing but summation for the k ranging from minus infinity to n H of k. Substitute the values. Now it is further simplified. It becomes, we can break this expression into two parts, and this minus 1 raised to power k is the common term, which is multiplied by two shifted unit step functions. So accordingly we can change the range of this summation operator, that is for uk plus 2, the range will be k from minus 2 to n. The value will be minus 1 raised to power k minus summation k is equal to 3 to n minus 1 raised to power k. Alright. Now again, further doing some mathematical manipulations for the ease of simplification, we can write the summations as, just changing the variables over here, m is equal to 0 to n plus 2 minus 1 raised to power n minus 2, we are replacing k by m minus 2 minus summation m from 0 to n minus 3 minus 1 raised to power n plus 3. Alright. Now simplifying these summation terms, we get 1 by 2 1 plus minus 1 raised to power n. Similarly 1 by 2 1 minus minus 1 raised to power n is equal to 1. This is the final step response for the given LTI system. Moving on to the fourth part, which is a continuous time LTI system. T is given as equal to p raised to minus e modulus of t. Okay. Similarly, if we the same way we did it for the discrete time LTI system, the similar relationship we can derive between the step response and the impulse function of a continuous time LTI system. This is the, let's say, system with impulse response h of t. It's a continuous time system. Input is xt, output is, let's say, s of t. St is the step response. So step response is xt is nothing but equivalent to u of t. So if we simplify the system equation of this system, we'll see that s of t, this case will be integration of the impulse function. So making use of this relationship, we'll find out the step response. So s of t equivalent integration e raised to minus modulus of t, so e raised to minus modulus of tau, t tau. Simplifying this integral expression, take the ranges from minus to 0 out of this absolute function. E raised to power tau, t tau, plus 0 to t, e raised to power minus tau, t tau. On simplification, find that this comes out to be 2 minus e raised to power minus t. Last part was again continuous time LTI system. The impulse response is ht 1 by 4 qt minus q of t minus 4. Again, we'll make use of the same expression that the step response is nothing but integral of the impulse response. Substituting the values, by 4 is common. Integral of unit step functions. These are the we'll get two terms which are nothing but integrals of unit step function. And we have already seen the property that integral of unit step function is a ramp function. This will be r of t minus r of t minus 4. This is the step response of the given LTI system. Next question is based on the autocorrelation function. The question is find the autocorrelation function, which is rxx tau of a sine wave given as x of t equal to a sine omega naught t plus phi, and where omega naught is equal to 2 pi by t. The question is to find the autocorrelation function of this sinusoidal wave. So let us simplify it. By definition, we know that the autocorrelation function Rx tau is nothing but equal to limit t tending towards infinity by t xt into x t minus tau t tau. We are using the autocorrelation function used for a power signal, because this is a sinusoidal signal which is a periodic signal and hence a power signal. So we are using the expression of this autocorrelation function that is being used for a power signal. So let us substitute the values of xt and xt minus tau and simplify it further. It becomes limit t tending towards infinity a square by t integration minus t by 2 to t by 2 sine omega naught t plus phi to sine omega naught t minus tau plus phi dt. This is dt not t tau. Please make correction of that. Okay, so let us simplify it further. Let us use some trigonometric identities here. Square by 2t and the integration minus t by 2 to t by 2, it becomes cos omega naught tau minus cos of 2 omega naught t plus 2 phi minus omega naught t dt. We used the trigonometric identity, that is cosine a sine b. It's further equivalent to limit t tending towards infinity a square by 2t cos omega naught tau dt minus limit t tending towards infinity a square by 2t integral of cos of omega naught t plus 2 phi minus omega naught t dt. And now this is a constant quantity. So, and the integral value will be t here in this case. If we solve this integral, the output will be t and a square by t cos omega naught tau into t minus, we solve this integral, it is the running variable here is t and this is cos 2 omega naught t over one time period. So the resultant will be 0. That is, we are integrating a sinusoidal wave over one time period, which results in 0. Hence the final answer is t square by 2t cos of omega naught tau. And so this is the autocorrelation function. So asked in the question, and further if you want to find out the power of this function, for power, find out the autocorrelation function at tau is equal to 0, and the power comes out to be a square by, which we already know that the power of a sinusoidal signal, of any sinusoidal signal, is amplitude square by 2. That is all for this video lecture. In the next video lecture series will start unit number 3. In particular, will start Fourier series. That is the only portion that needs to be covered in midterm. So we'll begin with Fourier series in the next video. video lecture series. Thank you.